Okay, so we have a region bound between this parabola, y equals x squared, the x range 0 to 2, and also the x-axis on the vertical. And this is going to be rotated around the x-axis. To form a three-dimensional solid. Okay, and our goal for this example is just to find the volume of the shape that we make. And whenever we're looking at a geometrical problem or a physical problem like this one, we always want to start by making a sketch of the actual object or the situation. So let's make a little two-dimensional plane. Okay, and then just do a quick sketch of this parabola from 0 to 2 on the x-axis. You're probably quite familiar with what this one looks like. If you plug in 0 here, you of course are at the origin. If you plug in 2, 2 squared is 4. So there's another point up here. Let's see, I think my connection was unstable there for a second. Looks like we're good now. And then we just connect this with a parabola, something like this. Okay, but we're going to chop this off at x equals 2, like so. And what we're going to do is take this region that I've drawn between the parabola, x equals 0 and 2, and then the x-axis on the bottom. So we have this, it's almost a triangular region, except one of the edges is actually a parabola. So what we're going to do is take this and rotate it out of the paper and back around until it passes, or until it meets this on the back. So imagine it coming out of the paper and then around the back. Then we can try sketching that as well. Let's see, how does that look on the camera? There we go. Okay, so imagine I've turned my plane up on its side so that we can sort of see the three-dimensional aspect of it, and put in some tick marks. Something like this. So it goes 4 up and 4 down. We're looking at a side view, so it's an ellipse and not a circle. And then something like this. Not a perfect picture, but we can kind of get a at least an image in our minds of the three-dimensional object. So it's kind of a bell shape. And what do we need to do next? Well, we want to use this formula here in order to find the volume. So we're going to need to think about what the radius is of each of the circles, each of the circular cross sections. But we actually don't have to do any work on this one because the formula for the parabola tells us the radius of each of my circles or each of my disks. Because this, if I just draw a vertical line here, this vertical line is going to be rotated around in a circle around the x-axis to form my cross-section, my disk. So this actually is the radius of my cross-section. And if you want to know the height of this little line segment, well, it's just the height of my function. So if this is, x, then the height is x squared. Okay, so now we can go to the calculus part of this problem. The volume is equal to the integral of pi r squared dx. We also want to think about the limits of integration. What are my limits of integration here?
0 and 2.
Right. So we're starting, well, this one was actually given to us in the problem. We're told the range for x, but on the geometry, we're starting at the origin, and then we're chopping it off at x equals 2. Good. Okay. And now we just have to plug in our radius x squared here. Okay, so that's the integral we need to do. And this is the kind of integral that you probably have a lot of practice doing from your first calculus class. X squared squared is x to the 4th power, 2 times 2. And really this pi, I usually write it here inside of the integral because I like keeping things organized like that, but you can actually just move it to the front, as you know, since it's a constant. So we're really just looking at the integral of x to the 4th. What is the integral of x to the 4th? Or what is an antiderivative for x to the 4th?
1/5 x to the 5th.
Good. So this is a power rule problem. Increase by 1, divide by the new power. So you have pi, and then the 1/5 x to the 5th. And then we still have our limits of integration to keep in mind. And I'll use this vertical slash notation. And then we plug in our two limits and find the difference. So we have pi over 5, and then 2 to the 5th power. What is 2 to the 5th power, anyone? Okay, no one wants to answer that one. What happens when we plug in 0?
It's 0.
Right. So we don't have to worry about subtracting anything. We just need 2 to the 5th times pi over 5, and 2 to the 5th is
32.
Good. So we have 32 pi over 5. Okay. So that's the volume that we were looking for. Any questions about this first example?
Yeah, you said it was going to be an ellipse, but if you rotate y equals x squared around the x-axis, wouldn't it be a circle?
So when I said an ellipse, I meant when you're drawing it on a flat piece of paper, it's going to look like an ellipse.
Mm.
Let's see, do I have a good example? Let's see, so if you look at my pen cap head on, it's a circle.
Yeah.
But if you look at it from the side, it's an ellipse.
I get it.
That's what I meant. Okay, any more questions? Let's see, maybe I'll let you see that again in case anyone's still writing. And I'll take a second to see if anyone else has joined us. No. Okay. Let's move on. So this next problem is not nearly as wordy. I just want to find the volume of a sphere. Okay, so maybe the first question should be, you guys probably already know how to find the volume of a sphere. What's the formula? What should our answer be at the end? Anyone know? Thinking back to geometry class or something. No, no one wants to guess. That's all right. Okay, there's the formula. I'm sure we've all seen it before. Okay, so what I'm asking here is not just to remember the formula. I'm asking you to use calculus to figure out what this formula actually is, or why this is the formula for the volume of a sphere. And I want to use what we're learning now. So volumes by revolution. Any ideas on how we could do that? How we can use this idea of rotating a shape? So here's a quick image of what we're going to be doing. It's kind of hard to draw a sphere on a flat piece of paper. So here's a picture from your textbook that does a pretty good job of getting the three-dimensional nature of it. So we're going to be slicing it into discs like they're showing here, and then adding up all those little volumes of little discs. There's something in the chat. Let's see. So someone asked, did we lose the teacher? Can you guys hear me?
That was me, just ignoring. You went silent for a while.
Okay, I was just opening up a new tab. Okay, so no one is jumping in, so I'm going to explain what I want to do. So what I want to do is take a half circle, a semicircle, and use that to find my volume. So in this problem, I didn't say find the volume of a sphere of radius 2 or something. So when I'm setting up my problem, it needs to work for a sphere of any radius. So when I make my half circle, the radius of my half circle is going to be r over here, and then minus r over here. And that means on the vertical, we also need to go up r. And then we'll do our best to make a half circle. Okay, so something like this. So the idea, in order to make a sphere out of this half circle, I'm going to take this half circle and rotate it around through my paper, back up through the back, around the x-axis. So I'm going to take each little vertical piece, like this one, for example. This vertical line is going to be rotated around the x-axis, and it's going to form a disk. Okay, so our formula, we're going to be using the same formula. Let's see, I'll reserve this space for some geometry kind of things. Down here, we'll just write it, the pi r squared business. What are my limits of integration going to be? So I'm rotating each of these lines around the x-axis. What are my limits of integration?
Negative r to r.
Good, yeah. So I can go ahead and fill that part in here. And this vertical line that I drew is going to play the role of the radius of each of my disks. And we have to spend a few seconds figuring out what this actually is. What is the radius? Let me write over here the formula for a circle is this one, the x squared plus y squared equals r squared. Okay. And we only want the upper half of this circle, and we want to figure out how high it is. So what we need to do is solve for y. I think we did this the other day, but in essence, you move the x term to the right, and then you have to take a square root. So you end up with y equals plus or minus the square root of r squared minus x squared. But for an upper half circle, we're only looking at positive y values, so we're going to ignore this minus half because it would be down here. So using this information, can anyone tell me what the radius is? What's the length of this line segment that I drew? Okay, so I wrote down the answer. This is the height of a circle. I've solved for y. And we're only looking at the upper half. So I want plus, and then the square root of r squared minus x squared. Okay. So I know my radius, I know my limits of integration. Now all I have to do is plug my radius in and then work through the calculus. Maybe we'll go ahead and move the pi to the front. And then put in the radius, r squared minus x squared. And conveniently, this square root is going to be squared, so we won't have to deal with the square root going forward. Which is nice, because otherwise we wouldn't be able to do this integral, or at least not very easily. So we really just have r squared minus x squared. Square and the square root cancel each other off. Okay, so now we need an antiderivative for this guy. Any ideas? No one's jumping in. That's all right. So the thing to remember when you're doing an antiderivative is that r, even though it's written as a variable, is actually a constant number. It's actually just the radius of my, in this case, the sphere. So we treat r squared like a constant, and the n antiderivative for a constant is just the constant times x, our variable. So bring the pi along, and then we have r squared x. Then we need an antiderivative for x squared. We'll use the power rule to get 1/3 x cubed. And then now we have to deal with our limits of integration. So plug in the 2, find the difference. So I'm just going to leave my pi sitting on the outside so that we don't have to deal with it until a little bit later. When we plug in positive r, we get r cubed, and then minus 1/3 r cubed. Put some parentheses around that because we're going to need to subtract. Minus r times r squared, that's minus r cubed. And then here's where we have to think a little carefully. We have minus r cubed, so that's 3 minus signs. And then we have an extra minus sign here. So overall we have a plus 1/3 r cubed. And then just do the arithmetic of simplifying this expression. I said r cubed and root r squared. That fixes it. R cubed minus 1/3 r cubed is 2/3 r cubed. And then bring down this minus sign. We have minus r cubed plus 1/3 r cubed. So that's minus negative 2/3 r cubed. 2 minus signs means we're actually adding. So we get 4/3, adding the tops of our fractions, 4/3 r cubed, and the pi is still out here. So we have 4/3 pi r cubed, and you can't see that. There we go. Okay, so we got the right answer in conclusion. So this method of finding volumes using disks matches up with our understanding of basic geometry, which is good because that means it works. Does anyone have questions about this example? Or is anyone still writing? I'll just take that as a no. Okay, so now things are going to get a little bit more complicated. So far, we've only been rotating around the x-axis. But of course, there's no reason why we couldn't rotate around, well, any other line that we might like to pick. We'll start off with this example. We're going to look at the curve from before, the y equals x squared curve. But now I want to find the volume of the solid generated. And then we're going to rotate the region. Let's see, I do have a little bit more space. Bounded by the curve from before, like I said, the simple parabola. But now instead of the region or the simple bounds from before, we're going to look at the line y equals 1 and x equals 3. And we're rotating about the line y equals 1. So, as always, we need to get a picture of what's going on. So we'll start by drawing a plane so we can figure out what region is being rotated. Okay, so we'll start by drawing the parabola. So try plotting a few points and then connect them. Like so. And then we can plot in the line y equals 1. So this is a horizontal line, like so. And it's a good idea to label these things. So y equals 1, my parabola is y equals x squared. And then the last bound is a vertical line, x equals 3. So x equals 3 is here, and we need a vertical line. So something like this. Okay, so now that we've plotted the three bounds, the three curves that form the bounds of our region, we can see what region we're actually interested in. So it's here, this sort of triangular shape in between our two lines and our parabola. So right here. So we're going to take this region and we're not going to rotate it around the x-axis. We're actually going to rotate it around this line, y equals 1. So we're going to take vertical cross sections here and then rotate them around y equals 1 back through the paper to make circles. So if we were going to draw a radius of a circle on this two-dimensional figure, it would look something like this, right? So let's try to start setting up our formula. We have v equals pi r squared, the integral of pi r squared. What are my limits of integration for this problem? What are the x boundaries?
One to three.
Good. So we're not starting at 0 anymore. This intersection where this line runs into my parabola, that's here at x equals 1. And then we're going to run over to this other vertical line at x equals 3. And then the next thing I need to do is figure out what to plug in for my radius. What's the length of this line segment? So we've come over to the right x. I know that this point is x squared. But what is the length here? Or the height of this point is x squared. What is the length?
X squared minus 1.
Good. So if I just said x squared, that would be the height from here all the way down to the x-axis. But we're actually stopping a little bit before we get there. So we just go from x squared down to 1. And to find that length, we subtract x squared minus 1. Good. So now that we know the radius for each of our cross sections, for each of our disks, we can plug it in and then complete the integral. Maybe go ahead and move your pi to the outside. And we have x squared minus 1 squared dx. Before we can find an antiderivative, though, we need to actually square this out. And this is a good point to remind you to be careful when you're squaring something or you're raising something to a power like this, because you're going to end up with cross terms. So we'll get an x times, or x squared times x squared, x to the 4th. Maybe I'll write it up here to illustrate what we're doing. Okay, so we get x squared times x squared, and then we get an x squared times minus 1, and a minus 1 times x squared. That gives us minus 2 x squared, and then we get minus 1 times minus 1. So a plus 1. So make sure you're careful. Don't forget about this term in the middle, the cross term. And then now that we've multiplied that out, we can continue finding an antiderivative using the power rule. In this case, x to the fourth, and antiderivative for that guy is 1/5, x to the fifth. And then the -2 comes along for the ride on the next term, and we get 1/3 x cubed and then an antiderivative for 1 is just x. Don't forget your limits of integration. Okay, and then in the interest of saving a little bit of time, I'm not going to work through all of the arithmetic here. I'm just going to go ahead and tell you the answer. It's 496 pi over 15. So if you are going to do this by hand, which I do recommend that you practice, you would end up having to find a common denominator between 5 and, or 1/5 and 1/3. And that's why you get a 15 down there in the denominator. Any questions over that example? Okay, let's see if we can do another one in the short time left. I want to find the volume, as always, of the solid generated by rotating the region bounded by y equals x squared again. And now we're going to look at a different bound, the y-axis and y equals 4. Okay, so this is the region, and we're rotating about a new line, the y-axis. Okay, so let's plot in our parabola again. Okay, and now we need the y-axis. It's already there, so we don't have to draw it again. And y equals 4. So that's a horizontal line up here. Okay, so now our region bounded by these three, or bounded by the parabola and then the two lines, is this guy here. And instead of rotating it around a horizontal line like we've been doing in the last few examples, we're going to rotate it around the vertical axis, like this. Okay, so you might be wondering what formula we're going to use. And really, it's no different than before. So if we want the volume by disks, because we're making disks when we rotate, about the y-axis, it's still going to be an integral of our cross-section areas. But now instead of the area being a function of x, because we have slices this way, now it's going to be a function of y, because we're slicing across this way. So we're now integrating with respect to y, but we're still looking at disks. So it's still pi r squared. So another important thing to keep in mind is that our radiuses now look like this. So we're finding a horizontal distance. So I need to figure out the distance from here over to here. So instead of the y coordinate, the y equals x squared, I actually need to figure out the x coordinate. So how far over is this point? And in order to do that, we'll have to rearrange this formula by taking the square root of both sides. So x is equal to now plus or minus the square root of y. But since we're looking at positive values of x, we're going to ignore the negative half. And this radius is going to be positive square root of y. And that's about it as far as the geometry goes. Otherwise, this is exactly the same once we get to the math. I think since I'm a minute over, I'll set up the integral and then let you guys finish it off. We can read off the limits of integration. Remember, we're going vertically now, so we're going to start at 0 and we're going to end at 4. And then we need pi r squared and then we can simply plug in our radius, which is the square root of y. Okay, and then that's, I think, a good stopping point, because everyone should be able to finish this off on your own. And this one is actually quite simple. The square root and the square cancel each other, so you don't even have to deal with those as you go forward. Are there any questions here at the end of class?